what I am working on, and I say I, but this is the experiments that we are going to discuss are a very large collaboration of people that are like-minded and working on the very same topics, and is the study of the way that electrons move inside materials, inside solid-state materials. This, of course, has a lot of applications in the electronics industry, so to create electronic devices that are faster and more energy efficient as we need more and more of them, and therefore this is towards more efficient electronic world. In the type of studies that we perform is using the photoelectron spectroscopy, which is rather a technique that is based on a rather old effect that is known since a very long time, which is the photoelectric effect. It was in fact one of the phenomena that brought through quantum mechanics, essentially, because it was understood it was possible to understand it only using quantum mechanics, and then in its history, then it has been transformed in a way to look into how the electrons move into materials. In fact, by extracting electrons from the material using light and looking at the energy that the electrons that come out have. And this is essentially the technique that is used. And in the particular case of my research, what we do is time-resolved photoelectron spectroscopy, meaning that we excite the system with a bright flash of light, and then with a second flash of light, we take the electrons out and study them. And this gives us information about how fast the phenomena can happen and how fast the electrons can change inside their behavior inside the material. Yes, so this goes a little bit more into detail, of course. SXP is the only machine in the world that can give us bright flashes of light in the X-ray range, which means that we are able to give much more energy to the electrons, and therefore they can come from deeper layers into the materials. And what we are studying in this particular experiment that we performed last week is in fact how, as a function of the distance from the surface of a material, the electronic behavior changes. So we use different energies of the photons, of the flashes of light, to get the information from different depths inside the material. Yes, oxide semiconductors are a family of materials that is extremely interesting for modern day electronics and new types of electronic devices, because when you have an oxide, the electrons have to move from, for example, the material under study in this experiment is zinc oxide. So the electrons have to go from the atoms of zinc to the next atom of zinc by crossing through an oxygen atom. And in doing so, they have to move through the different electronic orbits around the different atoms. And this creates a situation where the movement of the electrons is extremely sensitive to external perturbation, to things that we can change from outside. And this gives us electronic devices that can respond with very large changes in resistivity or conductivity, or that can even have very exotic properties, such as magnetism, superconductivity, and ferroelectricity, with very small applied changes that we have to do in order to obtain this very significant response. And so understanding both how this works and how quickly we can change this, it's extremely important for new electronics. And the applications are, as I mentioned, to create more efficient and compact electronic devices.